A normal star loses about 1% of its brightness when a Jupiter-sized planet crosses its face. KIC 8462852 lost 22% in a single dip, lasting days, with no clean shape and no repeating signal. Astronomers called it Tabby star, after Tabitha Boyajian, who first flagged the anomaly in 2015. The dips were not periodic. They were not symmetrical. Nothing in our catalogue of stellar behaviors predicted them. And the question that opened the file then is the same question still sitting on the desk now. What is passing in front of that star? The Kepler Space Telescope watched roughly 150,000 stars for 4 years, measuring brightness with extraordinary precision. Tabby star sat among them, 1,470 light-years away in the constellation Cygnus. Most stars dipped in clean, predictable curves. This one fell off a cliff. One event dimmed the star by 15%, another reached 22%. The dips lasted between 5 and 80 days, with no orbital rhythm a planet could produce. Citizen scientists at the Planet Hunters project flagged it by hand because the algorithms threw it out as broken data. The shape of the curve was not a sphere crossing a disk. It was something irregular, something with edges. The first natural explanation was a swarm of fragmented comets, thousands of them broken apart, drifting across the line of sight. The math almost worked. Comets could produce irregular shapes. They could explain the depth of a single dip, but they could not explain the count. To dim a sun-like star by 22%, the swarm would need to be implausibly vast, implausibly cold, and implausibly silent in the infrared. Warm dust glows. Spitzer and Wise looked for that glow in 2015 and 2016. Some theorists suggest the comets had simply moved on. The infrared sky around Tabby's star was, by every reasonable measurement, clean. Then Bradley Schaefer pulled the photographic plates. Harvard's archive held images of this same patch of sky going back to 1890. Schaefer's analysis, published in 2016, found that Tabby's star had been steadily dimming for over a century, losing roughly 14% of its brightness across 100 years. No comet swarm explains that. No dust cloud drifts that slowly. The short dips were strange. The long fade was stranger. Imagine a structure being built across decades, segment by segment, each new piece adding shadow. The story goes that natural physics can still account for it, but the contortions required keep growing. Jason Wright at Penn State raised the option no one wanted to raise first. A partially completed swarm of orbiting collectors, what Freeman Dyson described in 1960, would produce exactly this signature: irregular dips, a slow century-scale dimming, no infrared excess if the collectors radiated waste heat away from us. Wright was careful. He called it the hypothesis of last resort. But the resort is where the search has ended up. Every natural model proposed since 2015 has required new physics, missing dust, or coincidence stacked on coincidence. The question now is not whether the star is strange. It is what kind of strange we are willing to accept. Tabby's star is one shadow held still long enough to study. The dimming is slow, structural, almost patient. A silhouette that takes a century to draw itself. In the next video, the opposite case, events that last a single millisecond and release more energy than the sun produces in 100,000 years. Magnetars, fast radio bursts, the screams at the other end of the spectrum. Subscribe if you want to follow the rest of this catalogue. The silent shadows and the violent flashes belong to the same investigation.